This is the second part for the final project. So now what you're going to do is that you're going to choose the how do we do this? Yeah, we're going to choose 10 of these, half of it. So let me put it everything in the same color. Yeah. Let me place a little number. So it will be a little easier for me to count down. So let's say because of randomness, only half of them were able to reproduce. So let's just copy paste the first one. This is going to be here. Second generation. Okay, I will take this out, the numbers. So what I want to do is to say that these two are going to be a partner, whoever they are. These ones are going to be the partner. These ones are going to be a partner. So we got 5 partners. Yeah, so we have to choose 10 of the original population and group them in pairs. Each couple will have, guess what, 4 kids. Since we are talking here about tigers, we can say cub. So we'll have 4 cubs each one. So you're going to do, guess what, the Punnett square for each of them. Punnett square time. Yeah. But let's keep it easy. What I recommend you to do, I mean, you got internet. So look for Punnett square calculator. So here we go. We got the Punnett square calculator. Hey, look at that. It's the same page. Let's just say the number of traits in cross, only one of them is going to be something like this. The parent one, in my first case, is this one. So I leave it like that. In my second case is this one. So I will have to do it something like that. And it's going to show me the genotype. As you may notice, this is going to be the result. Again, you can just take a picture of this and post it in there. Well, I will just copy paste. And here, let me check that. Okay. Let me do something here. There we go. So you need to do that for each of these pairs. You have to post here the Punnett square. Let me just put it here. There you go. Let me just So you calculate the Punnett square for each of the pairs, for each of the lucky couples that were able to, well, have offspring. And then you got the results here. Once you have the results, the whole of them, you will have again 20 different individuals, 20 organisms, 20 tigers in my case. So you are going to calculate, guess what? Again, all this. Yeah. So you're going to tell me the frequency for the phenotype of that population, of that new population. For the phenotype, for the genotype, for the allele, and the Hardy-Weinberg. Give me 1 second. I will do this so you can see what will happen at the end. Okay, I'm back. So I already calculated all the frequencies for this population, and well, I already calculated the whole population. So remember, I take the first 5 couples, sorry, the first 10 individuals, and I make 5 couples. You can take, well, 5 from the top, 5 from the bottom, or the 10 that are in the middle, whatever you want. It doesn't matter. For each of them, you will have to do the Punnett square. You have to make the pairs. You have to calculate the probability of having kids. They will have 4 offspring. Let's just say that, well, everything will be perfect, ideal. That's the word I'm looking for. So I already got all the offspring for this second generation. So let's just say that that's died because reasons. And well, only the second generation is there. So we had here the full population, 20 different organisms, new individuals. Oh my God. That will be here. So I counted down. The 60% of them will have the dominant golden phenotype. 40% of them will be white. Pretty amazing if you ask. Then I calculated genotype frequency. 40% of them will have the homozygous recessive. 20% will have the homozygous dominant. 40% again will have the heterozygous. Pretty amazing, you know. For the allele frequency, 16 out of 40, that is the 40%, will have the dominant trait allele, and the 60% of them will have the recessive allele. After that, I calculated the Hardy-Weinberg equilibrium. It changed a little. If you compare that to the first one that I got it here at the top, it moves a little bit around the table. So from that, I will compare again. For the first one, the dominant homozygous here is going to be 16%, but if you compare with that, it's only 20%. The other two is going to be heterozygous 40%, 48%. For here, the heterozygous is 40%, almost that. And for here, it's 0.36. So we are very close. I mean, pretty sure that everybody will have something different from the Hardy-Weinberg equilibrium. But maybe somebody will. I don't know. It's math. It can happen. It's not very probable, but it can happen. And in this case, the population is still evolving because it doesn't match the Hardy-Weinberg equilibrium that I got. Yeah. So that's gonna be your project. Just make sure that you do the Punnett square for each of the couples. That you calculated the phenotype frequency, the genotype frequency, the allele frequency, and the Hardy-Weinberg equilibrium equation for both of them, the original and the second generation. And don't forget to write down a conclusion about the experiment. Remember, everything here is just the idea. In nature, it's a little more random sometimes. Um, well, if you want to have extra credit for this activity, like yeah, extra something, um, you can go ahead and tell me how the population that match the Hardy-Weinberg equilibrium will look like. How will be the genotype of the population? There we go. This is for extra point. If you want to solve it, that's okay. I won't tell you how to do it. The only thing that I will tell you is that, well, you have to choose this one, the last one that you calculated. And from that, you have to tell me which one will be, well, this one is the genotype frequency. The allele frequency is going to be this one also. So the only one that will change is this one, the phenotype frequency. And because of that, also this one is going to change. And you have to tell me how it will look like what is going to be the genotype for all 20 individuals. So that's going to be all for your second project. Pretty sure that you can do it in 2 hours or less. If you got any more questions, you can look for me. That will be all. Thank you so much for paying attention.